Okay, now, hello everybody. This is week 8 for our laboratory session. Now, today's talk will be about the PID controller and the PI-PD controller. Now, basically, we call it PI-PD, but you can see that there is a proportional part, integral part, and derivative part, which means that this is basically a PID controller. But the reason that this is called PI-PD is because of its structure, because there is a degree of freedom that is different here. Therefore, this is basically a PID controller, but also not really a PID controller. We'll see. Now, we have a very basic system here, a first order system. And again, we have a settling time requirement, overshoot requirement. This time we have 0 overshoot requirement, which means that the zeta value should be equal to 1. And then we'll go ahead and design a PID controller and then look at its closed loop step response, polyron map, etc., the usual stuff. And once we're done with A, what we will do is we will take a look at the PI-PD controller, how it is different, what the advantages or maybe the disadvantages of the PI-PD controller is. Let's get right into it. Let's define our system. Maybe I might increase the zoom a little bit more. So the transfer function is 2. And the symbolic version is also this one here. So what was the settling time requirement again? 2 seconds. Zeta is equal to 1 because 0 overshoot. Therefore, we can directly calculate what omega n is, Ts times zeta. Now, we can form our desired closed loop polynomial 2 times zeta times omega n times s plus omega n squared. And then we have a first order system. Using a PID should give us a second order system. So it should not be a real, it should not be a big deal here. So let's define our PID parameters, Kp, Ki, and Kd. And then also our controller, Kd times S plus Kp plus Ki divided by S. You can also write KdS squared plus KPS plus Ki divided by S. It's basically the same. And then we have the closed loop, FSS times GSS divided by 1 plus FSS times GSS. So, of course, we'll look at the numerator and denominator of our closed loop. So let's see. So now zeta is equal to 1. PZS looks like this. And we have a second order closed loop, therefore it will be fairly easy, hopefully. So what we have to take into account is that the fact that the S squared term has a coefficient 5, so we should get rid of it. So let's call it all. Take the coefficients of PCS. And then let's normalize the polynomial here with the first coefficient, because this is the highest order term. And also we should maybe put a semicolon here. So that's one thing, and the other thing is that we need the coefficients of PDS, and this should be equal to the polynomial here. Now, let's display the problem here. This VPA problem Python. There we go. Now we can see that in terms of design, it seems like we have a normalization here. 144. Yeah. Now, of course, it's possible to multiply everything with this. And then we have 5kd plus 5 equals 1 here, as far as I can see here. So this would mean that we already have kd defined here, because this sum should be equal to 1. Normally, you don't see really this thing here, because we have most of the time s cubed, s squared on its own. There's no unknown in it. But it seems like using a PID control for a first order system causes this thing here. But I can directly see that kd should be, or 5 kd plus 5 should be equal to 1. So kd is probably a negative value. So minus 0.8 seems to be working here. Then we should plug them in here. And then 5kp plus 1 should be 4. 5ki should be 4. So you can see that we have basically a PID controller for a system. Since for this problem, especially, we have 3 unknowns and 3 meaningful equations, which was not the case up to this point, because we did get rid of the first equation here. That was a trivial equation. And then we were left with 3 parameters and 2 equations. But here, that's not the case. We have a specific value for kd, because this is not trivial anymore. So this is an interesting case. Therefore, we are examining it here. So let's solve this. Let's solve the problem here. And let's see. So solve seems like there is one solution, which I expected. So kp val equals, now we're converting them to double, sol.kp, ki, and kd. So since we have that, what we can do is we can go ahead and define our controller. This is kd, kd val, kp val, and ki val. And then a closed loop, of course, feedback, s times gs, comma 1. Now, let's also acquire the step response here. And close your map. Because we will use a figure here and show the results. So let's define the figure, subplot. Let's have them side by side. Let's plot the step response here. And let's also get the step info here in order to show the settling time stuff. Info equals step info. Yes. Let's update the title here and show a message that shows us what the settling time is. So convert it into string info.settling time. And then plus, and then maybe overshoot plus string info dot overshoot, and this seems to be all right. Now let's plot the false zeros. So let's plot the false first. Go. Now the zeros. Circle. Since we know what omega n is and zeta is equal to 1, what we can do is we can go ahead and use an S grid here, the zeta value, comma omega n. So we have also the omega n lines here. All right, this seems to be okay. So let's run this. And there we go. Now this is the result here. So let me place this here. Now what we can see is that in the y-axis here we have 10 to the power of -8, which means that this is close to 0. Now This is a numerical thing here. If you have poles on top of each other, then you have basically, let's say, roots of, let's also have the convolution here. So if you have, for example, 1, 1, and 1, 1, then you have poles at -1. They are coinciding here. If you have, there's no convolution, 1 to 1, again, you have -1 and -1. If you have a very slight numerical error here, you will get a slight deviation from the poles here. And if you have, for example, a third order one, let's change it to this, you'll see that MATLAB also displays here some plus minus because they are conjugate pairs, and then there's a real part, but they are on top of each other. But this becomes more and more numerically sensitive. Therefore, sometimes if you use PZMap, you'll get some 10 to the power of -8, so something that's negligible, that's really small. Therefore, what we can do is we can just update the y-axis in order to see that they are in fact on the real axis, not really on the complex axis here. So what we can do is we can just say that the y limits here of our figure should be between -1 and 1. That would be just graphically more accurate, but it's not really that big of a deal. But you can see that they are coinciding here. And maybe we should also change this x limits here to -3 and 1. Seems to be better in terms of visualization. So -3, 1. There we go. Now we can see that, of course, if we have zeta 1 and omega n equal to 2, it seems like S-grid does not display it very well. Interesting. Why is there a problem there? Let me see. S-grid zeta omega n. Maybe we should also put in another one. For some reason, we don't really get this effect that I'm looking for. Interesting. Maybe the zeta value is here a problem. So let's try that. Maybe if we add something else like 0.5, 1, maybe that's going to help out. Let's see. Yes, for some reason, S-grid is not really working here. Interesting. Well, let me just leave it out because it's not really helping us. Okay, now here we have basically the origin, the j omega axis. We can also plot it manually, but it's not really that important at this point. Since we have a second order system, we have two poles, they are on top of each other at -2, which was expected because we have zeta equals 1. And omega n was equal to 2 because 4 divided by 2 gives us setting time of 2. But we have two poles. One of them is on the left half plane, one of them is on the right half plane. And these zeros are more dominant in this case. So again, we have a dominance problem. And you can see that for some reason, the step response here starts at a negative value, and then we have a certain overshoot, and hopefully we have a steady state value of 1. Seems like we need a little bit more in terms of time here for the simulation. So let's have it 2 times settling time. And you can see it's becoming equal to 1. But again, it doesn't show us. Interesting. Yeah, now you can see that the overshoot value is not really what we are looking for. And we are designing a PID controller. The bad thing here is that if we look at the problem itself, we have no other choice because KD is directly equal to something, and then we have KP and KI. 3 unknowns and 3 equations. Seems like there's not much to do. And well, if we have KD negative, that's the biggest problem here, because the PZS here, if we have KD negative and KP and KI positive, which is, by the way, the case for KP values equal to 0 even. So we have KI 0.2. You can see that one of the roots is on the right half plane, one of them is on the left half plane. So yeah, in terms of settling time and overshoot, we are not able to meet the requirements, and a PID controller seems to be a bad choice here. So now, in terms of poles, we are basically happy because we have -2 and -2, just as we wanted them. But the zeros here are placed by the designer here, or by the controller. So we've placed them there, but well, we're not really happy with them. So what can we do? The big question here is to get rid of the effects of the zeros. Now, usually or normally what we want to do is we want to push them on the left side here and then even further to the left. But that's not really possible here. We didn't even use tabulation because we have no free parameter here. So at this point, what we can do is we can do the following, which is going to be a bit interesting. Now, now what we can do is we can do the following. We have a PID controller, but what if we use a PI-PD controller, or if we update our PID controller a little bit? Because we will again have the proportional part, integral part, and derivative part, but the aim here is to get rid of the zeros effects. So how can we do that? Well, before I dive into the PI-PD controller, let's assume that we are only designing a PD controller. So if we have a PD controller and 1 divided by S plus 0.2. So this means that KDS plus KP will be our controller, and then we'll have a closed loop that should look like this: KDS plus KP, and then divided by. Since we have a PD controller, the denominator will also not really change that much. Let's assume 4S plus 5 for some reason. It's not really that important. So again, here we have a 0 and a pole. Probably the pole that we're choosing here will meet the requirements. Let's assume that. But we will have, again, a 0, which is basically the same case that we are facing here. So is there a better way of using the same PD controller so that we don't get basically the effect of the zeros? So how can we update the PD controller? Any ideas? So we have a PD controller, we will use it again, but instead of having KDS plus KP divided by 4S plus 5, let's update the PD controller, or let's change the way that we use the PD controller so that we don't have any 0 in the closed loop. The idea is basically to use the PD controller not in the loop here, and GS don't use it here. Let's take this controller like this and place it on the feedback loop. How about that? So GS will be again there, but the controller will not be on the forward loop, it will be on the feedback loop. Would this mean anything? Would this be helpful in some way? Let's see. If you have this system and the controller like this, what is the closed loop transfer function? What will it look like? What is the expression for the closed loop? This would be the closed loop here. GS divided by 1 plus PD times GS. In this case, this numerator part will not be present here. But since the denominator part basically is the same, we will get again the same characteristic polynomial. But then we wouldn't have that. We would have 1 divided by 4s plus 5. Which is, in terms of poles and zeros, very helpful. Because we don't have to deal with the zero itself. It's not present anymore. We don't have it anymore. Basically, this approach can be applied to the PID controller too. You can take the PD part, place it in a feedback loop, and use this as a plant for the PI controller, and build another loop. So we have another loop, an outer loop here, like this. There will be another loop, but we have basically decomposed the PID controller in terms of PI and PD parts. We've placed the PD part into the feedback loop, and then we have the PI controller with another loop. So we have basically 2 loops now instead of 1. But this will hopefully get rid of the zero of the PD controller. Why? Because if you have a certain PID controller, what you can do is you can just take it, decompose it into its PD and PID parts. So S plus Z2, let's call it Z1, divided by S. So this is basically, let's put a K here, K times S plus Z1, S plus Z2. Now, this is a PID controller. But what you can do is, instead of using this, you can go ahead and say, let's have K1 times S plus Z1, and then K2 times S plus Z2 divided by S. If K is equal to K1 times K2, you will get the same transfer function out of this. It's basically the same. The only difference here is that we have basically used a PD controller and then a PI controller, but it's again the same controller. And if you have a system here, GS, the closed loop, the numerator, the denominator will be the same. Nothing to change really. We've taken them apart, used the PD part and PI part. The only restriction here is that the gain distribution here should be corresponding to the same gain. Since we have them in a series, we should multiply the gains here. So if this is okay, then understanding the PI-PD controller will be easy. Because the only thing that we do here is that we take this and put it in the feedback loop, and that's it. So instead of using the PI controller, the PID controller like this, let's have PID here. Instead of using this, just build it again. Instead of using this, what we will do is we will do the following. We'll get the PD part and then build another loop here. Let's do that quickly. Well, then construct another loop out of here. Like this. Let's use the PI controller like this. That's the connection that we're looking at. So what will be the advantage of using this structure here? Well, as I've talked about the PD controller, here, if we calculate the closed loop of only GS and PD, we'll get basically no zero in the closed loop of this inner loop here. And then we'll use the same, or the closed loop transfer function of this. So that means that it will be converted into the following. So we'll have, let's say, TS inner. So there will be an inner transfer function here. But if we calculate the closed loop, we'll use this here. Now, since this has no zero in its transfer function, we'll then use the PI controller, calculate the closed loop, and what we will end up in is that we will have basically 1, 0, and the characteristic polynomial. So this would look like this, k times s plus, let's say, z2, divided by PCS. So this would be the closed loop of this, but in the PID controller, what we'll have is we will have this. So getting rid of one of the zeros is a big advantage, a huge advantage here, because you have to keep 1 0 away from the dominant region. So that's nice. But that's not all of it. We still have something left here. We did get rid of the 0, but what about this 0 here? Note that the PI controller is left, and here somewhere, did I remove it? Seems like it. Here somewhere, I've talked about the fact that we can use s plus z1, 1, and then times k2 times s plus z2. Now, and divide by s. So let's say that this is the thing. Now here, or in this case, let's use this because Z2 is defined here. Now, one restriction is that K1 times K2 should be equal to K, but we don't know what K1 is and what K2 is. We have the only restriction that the multiplication of them should be equal to the original gain or proportional part of the controller. But here we have just a multiplication. That's a limitation. Which means that we can choose another parameter here. We can choose K1 or K2 as we wish. And as soon as we have K1, for example, we can calculate K2 using this relation here. How can this be helpful? Now we use the feedback loop for the PD controller part. That's nice. Got rid of 1, 0. We have still the gain left here. We didn't decide on the gain of the PI controller and on the gain of the PD controller, but their multiplication has a certain gain. So, well, we can use this, one of the gains here, in order to decide on the 0 of the PI controller. So not only did we get rid of one of the zeros, we also are able to place the second 0 that's present in the closed loop as we wish. This means that basically these zeros will not cause any problem anymore if we use the PI-PD connection, because we will get rid of one of the 0 and place the 0 that's left accordingly. So that's really powerful in this case, and we'll see. Now, let me demonstrate to you a simple fact. Let me just create another script here. Let me demonstrate to you that I'm not really wrong about this. Let me show you that I'm right about this, because don't even use anything. Let's just decide that we will use the loop that I've already talked about here. Let's use the PI-PD controller from the beginning. So we have our transfer function, or PDS, but at this point, I'm going to define a KPI and KPD, which will correspond to the controllers. So this is the gain of the PI controller, and this is the gain of the PD controller. And then we will have KI and KD. In this case, let me also define it down here. In this case, the PI part will be KPI, let me write it like this, KPI plus KI divided by S. So that's a PI controller. Let's have FSS-PD, which would be KD times S plus KPD. So I'm just using a gain for the PI controller here, another gain for the PD controller, but the derivative and integral parts are the same for the PID controller or for the PI-PD controller. Now, of course, the closed loop now will not look like this down here. First, we will use the inner loop. So we need to calculate the inner loop here. And the inner loop will be calculated using this, 1 plus FSS-PD times GSS. And then, since this is the inner loop, we have another outer loop, which uses this as the plant and is a PI controller. So therefore, the actual closed loop will be then look like FSS-PI times the inner loop divided by 1 plus FSS-PI times, again, the inner loop. And then we will have PZS, PCS, the coefficients of them, and then we'll solve it. Let's stop at this point. And let's don't even solve it for now. Let's just look at the problem itself. Run 2. So now, again, it seems like 5 plus KD, 5 times KD plus 5 should be equal to 1 because we multiply all the equations with 5 KD plus 5. But you can see that the number of unknowns are, or the unknowns are KP, KI, KD, or KPD, KPI, KI, and KD. So we have 4 unknowns and 3 equations at this point. So it could mean that we could use basically tabulation as we did before. But you can also see that the restriction here is not really that KPI and KPD are that free because this is basically KP here. So 5 KPD plus 5 KPI is basically 5 times KP. So the sum of these are basically the proportional part again. So we can just use the PID solution here. We know what KP should be, KI should be, and KD should be. That's again possible. But since the sum of KPD and KPI are equal to some value, again, we can use KPD or KPI to choose the gain and then calculate the other one. So this is interesting because a lot of things have changed, but also nothing did really change. So yeah, the KD and KI values are the same. Therefore, you can use the same values from the PID controller, but you can decompose the proportional parts because their sum is equal to something now. So let's make a wise choice. Therefore, I'm not really going to define a whole thing here like this. Instead of this, I'm just going to go down here, PI, PD, and I'm going to use the KP val, KI val, and KD val values here, but I'm going to generate different controllers. So now, if I want to define the PI controller, I know that we will have a pole at the origin. So yeah, KI is already KI val, but what should be KPI val? Because once I've defined that, I will define FSPD here, and it will look like this. So I have KD val and then KPD val. So yeah, I have to decide on KPI val and KPD val. But their sum, KPD val plus KI val, should be equal to KP val. So what would you choose for KPI val? Or how should we decide on KPI value? Well, we know where our pole is. We want to place the pole at -2 here. So let's pick a 0 that's going to correspond to a dominant pole placement strategy. For example, if it's at 2, 10 times 2 would give us 20. So if we would place our 0 at s equals -20, that would be a good choice, I guess. At least 10 times a dominance factor would give us a good result. Since we don't have any other 0 than the 0 of the PI controller, this should work. Well, if we want to use 20 as the 0 of the PI controller, can we just calculate KPI val? We can just use the fact that here we have basically S and we have Z here, but 1 and Z basically, and this should be equal to 20. So if we already decided that this is KI val, then this should be KI val divided by 20. We're not changing KI val, but we are determining the gain part here. So therefore, what we can do is we can say KPI val, and KPI val should be KI val divided by 20. According to this relation, KPD val would be KP val minus KI val, KPI val. So we take the integral part, divide it into the dominance factor, 20 in this case, or 10 times the dominance factor times omega, or the real part of your dominant poles. And we get a PI controller gain. We use that gain subtracted from the original proportional part, and we get the PD gain. Şöyle, bağlantıyı nasıl kurduğunla alakalı denklemlerden toplamı çıktı. Seri olarak bağlasaydık çarpımı olacaktı. Biz seri bağlamıyoruz ama feedback loop'unu alıyoruz ya birine. O yüzden. Seri bağlasaydık çarpmamız gerekirdi. Ben orada sadece ayrıştırabildiğimizden bahsettim. Feedback loop'una koyarsak oradan ne çıkıyorsa o. Oradan da toplamları çıktı. The question was that why didn't we use the multiplication of KPI val and KPD val, because that should be equal to KP val? Well, if you use the PI and PD parts in series, that's the case. Then you have to multiply the gains. But if you use the PI-PD structure, it's not using the series connection here. It has a multiple feedback loop structure that you should memorize, for example, in this case, because you have to be careful about the fact that the PI-PD controller is not using one loop, it's using 2 loops here. One to use the PD controller and then an outer loop for the PI controller. That's really important here. Now here, according to the closed loop transfer function, we've seen that in run 2 that the sum of them is equal to the proportional part of the original PID controller if you're using a base PID controller. Now, once we've decided on that, here's also another question, by the way. What if KI val is a certain value, let's say 2. 2 divided by 20 gives us 0.1. What if KP val is 0, which is in this case? Then we get KPD val a negative value. Isn't that causing a problem? Because we have a negative value for the PD controller as a gain. Isn't that problematic? Because most of the time, for the zero polynomial, for PZS, we want the zeros on the left half plane. But since PD controller is in the feedback loop, it doesn't really matter. If it's a positive gain, if it's negative gain, it will only change if we are using a positive feedback or negative feedback. But it will not affect the zeros because they are not present in the closed loop. So those are inner dynamics that we don't really care about here in this case, and therefore it's not a problem. If KPI value is negative, then we'll place a 0 on the right half plane. But other than that, we don't. So let's see what the response of the PI-PD controller will be. So instead of looking for that, let's call this TS inner and calculate the first loop. So GS and then FSPD. FSPD and GS. This is the inner loop. And then we have a PI controller and this inner transfer function here. So therefore, feedback, we have FSPI times TS inner, comma 1. Now we can repeat all the stuff here. Let's assign this to a variable in order to get access to them. And let's repeat this here. And plot everything. Let's see. So for AX1, do this, don't touch that. So AX2, let's assign a blue color to this. There we go. And let's also display the info here in the command line instead of putting that on the title. So we didn't color the first one. Let's fix that quickly. There we go. Now here, we can see, or we can also not see the 0. Let me also quickly change that. Instead of using -3, let's use -21, because we have a 0 there. There we go. Now here we can see we have the same poles, they are on top of each other. The PID controller did use -2. The PI-PD structure also uses -2 for the closed loop poles. But we've placed a 0 at -20. This is the 0 of the PI controller. And we don't have any other 0. And as you can see, the response looks smooth here. The expected shape is there. And we have the settling time value and the overshoot values that we are looking for. Well, overshoot is 0. This is nice. The settling time is a little bit off, but that's not really the issue of the settling time formula. Well, basically it is. It's not a problem of dominant pole placement. It's the problem that the settling time formula is not really valid for zeta equals 1. It's for underdamped systems, not critically damped systems. But you can directly just adjust for that. So let me pick another coefficient. Instead of 4, we can maybe increase that a little bit. Let's say 5 maybe, and that'll get rid of the problem. So you will get 2.2 if you increase a little bit more, and to be exact 5.83, then you should get almost equal to 2. Maybe decrease it a little bit, increase it. You could just adjust for that. Yeah, you have 1.95. I can go ahead and increase the performance here, but that's not really that big of a deal. But you can use 4 divided by omega n in order to choose your poles, but you can also toy a little bit around with this. For critically damped, you can use 5.8 as an approximate settling time formula. For the first order, you know already that it is 4 divided by 3.91 divided by omega. So yeah, that's not really what I am trying to mention here. You can see that we have basically 2 seconds of settling time and a much better response here. Of course, you can change the dominance factor here. You don't really have to use 20. You can also use maybe 10. And you can see it still works. It's not really, oh, it did not update by the way. Oh, this is just, yeah. There we go. Now you can see it is placed on -10. And again, we have a satisfying result here with 1.89 and yeah, 0 overshoot basically. So yeah, the PI-PD controller is basically very useful in this case. It allows us to place a 0 independently and get rid of the other 0. Therefore, if you look at the closed loop here, you can see that we have only 0.029 s plus 0.29. And we can also see that there's a 10 times factor here. And we have a second order transfer function, which was not the case for the PID controller. And you can directly see what the poles are, what the zeros are, and the gain here. In terms of root locus, oh, I did, by the way, close that. But in terms of root locus, what does this PI-PD structure give us, or what does it tell us? Let me instantiate my MATLAB again. So if you're looking at the root locus, oh, this was not. In terms of root locus, what does PI-PD tell us? Well, most of the time, if we have a certain open loop and we're talking about the root locus plot, what we do is we look at the poles and zeros of the transfer of the controller and add them to the open loop system. For example, if we have a first order controller like this, then we say that we are adding a 0 at -1 and we are adding a pole at -4. Therefore, the root locus is updated. In this case, using a PD controller in the feedback gives us an inner loop transfer function, which is basically updating the root locus again, but using a feedback loop. And then we're using this for open loop in order to design a PI controller. So there's a two-step root locus manipulation here. First, using the PD controller, we get a certain inner transfer function here. And then we, again, add a pole at the origin, try to add a 0 out of the dominant region, and then choose a P-type controller, basically. So we are not designing the PI controller to the original system. We use a PD controller to manipulate that so that it allows us the best possible dominant pole placement strategy. So therefore, using a PI-PD controller is really important. It is basically a PID controller, but it has an additional freedom to it that allows us to place the zeros. Most of the time, we have to stick with the PID controller zeros. If we are using tabulation, we still try to push them out of the dominant region. But in this case, we are able to place the 0 as we want.
Each PD kontrolörü geri besleme yoluna koyunca sadece kutuplar eklemiş oluyoruz ya.
Kutupları hareket ettirmiş oluyoruz aslında. Bir şey olarak, mesela davranış olarak şöyle düşün. Geri yolda bir PD kontrolör aslında çıkışı ve çıkışın türevini geri besleyerek kutupları hareket ettiriyor. Kutupları başka yerlere götürüyor. O oluşan sisteme PI kontrolör tasarlıyorsun. Orijinalde sisteme PI kontrolör tasarlaman lazım. PI gibi davranıyor aslında burada PI-PD.
Mesela geri besleme yolunda PD kontrolör koymak yerine normal iç çevremde GS'in önünden sadece kutupları olan bir kontrolör koysaydık olmaz mı? Yani bir şey yapmaz.
Ama kutup eklemiş olursun o zaman. PD kontrolör kutup eklemiyor ki. Şimdi 1 bölü S artı 0,2 miydi mesela burada sistemimiz? 1 bölü S artı 0,2 var burada. PD kontrolörle hem sabit terimi hem S'li terimi değiştiriyorsun. Sonra ortaya başka bir sistem çıkıyor. Ona PI kontrolör tasarlıyorsun ama hala derece artmadı. Senin dediğinde bunun önüne gereken kutupları koyarsak 3. dereceden olur 2 kutup koyacağımız ya da bir kutup koyarsak 2. dereceden olur. Diyorsan ki kutup 0 götürme yapabilir miyiz? O zaman tümüne zaten kutup 0 götürme yap model işlemindeki gibi. İç içe feedback loop niye koyasın o zaman? Burada değişik bir şey var. Burada şu var. Ya tabii ben burada şimdi düşük dereceli de yaptım da 4. dereceden bir sistem var. Buna PD kontrolör uygulayarak biraz kök eğrisini değiştiriyorsun. Yani yorum olarak söylüyorum tabii bunu. Normalde PID ile tasarlıyorsun, sıfırı yok ediyorsun. Bu aslında. Çünkü bizim buradaki amacımız kutupları değiştirmek. Evet, ama sıfırların etkisinden kurtulamıyoruz biz kontrolör tasarlarken. Çünkü sıfırı biz ekliyoruz ve sıfırı eklediğimiz yere kutupları çekebileceğimiz noktaya karar verirken veriyoruz. Keyfen karar vermiyoruz. Ama PI-PD gibi bir yapı, ekstra bir iç çevrim atarsak o zaman ne yapıyoruz? O zaman sıfırın etkisini sonra düşünürüz. Önce biz bir tasarlayalım. Sıfırlar kötü yerlerde de çıksa biz o sıfırları atarız. Birini atarız, birini uzaklaştırırız. Onu çözeriz. Onu bir dahaki loop, yani parçalayarak çözeriz onu. Önemli olan doğru kutupları atamayı versin bize diyoruz aslında PI-PD kontrolör tasarlarken. Yani PID'nin bir sonraki aşamasında hadi bunu PID olmasın da PI-PD olsun. Çünkü PID'nin problemi 2 adet şeyin olması, sıfırın olması. Bu 2 sıfırda gördüğün gibi mesela bu sistem için başka seçenek yok. Biri sağda çıkıyor, biri solda çıkıyor. Ters aşım yapması yetmiyor. Eksi büyük bir değerden başlayıp biri oturacakken çok kötü bir tasarıma sebep oluyor. Halbuki kutuplar açısından çok iyi bir tasarımdı. Sıfırlar işi bozuyordu ama sıfırların etkisinden kurtulunabilmesi için böyle bir yol var. Bu arada geri yoldaki PD kontrolör, PV kontrolör altında, Position Velocity adı altında kullanılan bir teknik. Yani hem konumu ölçüyorum hem hızı ölçüyorum. Ben bunların ikisini de kullanayım. O zaman istediğim gibi kutup atama yaparım veya istediğim gibi davranışı bir boyut daha eklemiş oluyorsun çünkü. İstediğim gibi kontrol edebilirim ya da daha özgürce kontrol edebilirim durumu var. Hatırlarsanız P tipi kontrolör için sıkıntımız neydi? Kök eğrisinin üstündeydik ve kök eğrisinin üstündeki başka bir yani olmayan bir noktayı seçemiyorduk. Ama bir tane terim PD kontrolör kullanarak bir terim getirerek ne yapabiliyorduk? Ben o zaman sıfır ekleyerek önce bir bükerim, ondan sonra üstünde hareket ederim gibi oluyordu. Burada da ona benzer bir davranış var. Ama burada nihayetinde amaç kök eğrisini bozup değiştirip PI kontrolör tasarlamak değil. Burada nihai amaç aslında sıfırlardan kurtulmak. Sıfırları yönelik bir şey bu. Ve çok kullanılmasının sebebi de aslında kutuplarla ilgilenip sıfırları da sonra halledebilmemizden geliyor.
Peki şimdi gösterebilir misiniz? İlk çevremde PD'yi geri besleme yönünde olarak ilk çevremin transfer fonksiyonu.
Şu inner'a bir bakalım istersen. Elde edilmiş haline de bir bakalım. Test inner. Şu şekilde bir şey oluyor. Normalde neydi? Şuydu. ZPK'ya bakalım bir de. Şu şekilde. Yani hem kazancını hem de kutbun pozisyonunu değiştirdi. Halbuki G şöyle bir şeydi. Yok, zaten tamamladık sayılır. O yüzden şey değil. Soru nereden gelmişti ya? İlk soru neydi? Çok şey anlattım şimdi.
Neden PD kontrolü geri beslemeye koyduk?
Tamam. The first question was that why are we using a PD controller in the feedback loop? Instead of that, what if we use just the pulse added to the system in the inner loop? Well, basically then we are again altering the system, but we are adding pulse. Now the PD controller here does not really add some pulse, but it uses the feedback in order to change the position of the loop of the pole or change the gain of the system. So we're basically altering the GS here. It becomes another system, and then we're kind of designing a PI controller. Another way of looking would be the following. We could also use a PI controller here, but only using a PI controller, we would not achieve that much because we have a zero of the PI controller and we will have a second order closed loop. But by using a PD controller before we use a PI controller, we alter the system and get the best out of it. Because if we have a PI controller, we would not decide on the position of the zero. It will naturally arise. Therefore, it would not be, maybe it would not be suitable for dominant pole placement. So therefore, using a PI-PD controller is somewhat between designing a PI controller, getting the benefits of that, and a PID controller. And the best thing about this is that you can just use a PID controller, just design a PID controller, aim for a PID controller. And if it's not working well, you can just opt your structure, change it to a PI-PD controller, because you are just concerning with the poles of the system. In this case, we achieved the best possible set of poles in the closed loop. The only problem was that we had some zeros that were troubling us. One of them was on the right half plane, one of them was on the left half plane. Therefore, using the structure, we got rid of those adverse effects of the zeros. Therefore, it's really easy. You don't really have to design the controller from scratch. You have a PID controller, take the proportional parts, divide it into parts where you decide on the zero of the PI controller, and then you can just use the relation and the fact that the sum of the proportional parts of the subcontrollers in this case are equal to the original PID KP value. So using that relation and deciding on the position or location of the zero, you have your PI-PD controller. But again, we have two feedback commands here, which points out the fact that we have one loop here with the PD controller and then another loop, outer loop for the PI controller. Well, this is basically also it for this week. I can show you a little bit about my notes, but there's also not much to it. You have, again, the codes, you have the PI and PD parts, and we are designing the controller here. Now, I have also given you basically the generalization here. And you can see that in this case, we have a negative KD val, but it's not really that big of a problem because it is in the feedback loop. It only maybe affects the type of the loop if it's a negative feedback, if it's a positive feedback. But other than that, we're not really dealing with that. And then we have this PI controller, and this is a closed loop. Here's again a comparison, and you can see that our closed loop looks like this in this case, and that's basically it. Now, if I'm not mistaken, next week we will be talking about some delay in the systems. Therefore, next week will be a much more packed week.